Hey everyone, and welcome to Chapter 2 of our Algebra Red course. In the first chapter, we covered some important terminology used in algebra. Now in this chapter, we'll use those terminology to build an understanding for one of the first concepts in algebra, and that's linear equations in one variable. Now you might already know that equations come up frequently in math contests, and also even in some everyday life situations too. So it's important to know what they are, and when to use them, and how to solve them. Now, linear equations in particular help us to build a foundation of how to set up and work with equations so that we can continue to expand on it in the later chapters too. So with that, let's jump right into it. First up, what is a linear equation in one variable? Well, we already defined equation in the previous chapter, and a linear equation in one variable is an equation with two properties. First, as the name suggests, there is only one variable, sometimes also called the unknown. Second, the equation is linear, meaning that the one unknown has exponent 1. Now, it's okay if we're not yet familiar with exponents. Those will be covered in later chapters. For now, we can assume the equations we encounter in this chapter will be linear. So let's take a look at some examples. First, we have 3x plus 4 equals 7. Here we see that there's only one variable, x, and the x has exponent 1. So this is a linear equation in one variable. Now, a more interesting example, we have 3 times quantity x minus 6 minus 5 times quantity 6 plus 3x plus 7 halves times quantity x over 2 minus 1 all equals to 5 halves. Here we see that there is again only one variable, x, even though it occurs in multiple places. That's okay, there is still only one variable, and in each place the x occurs it has exponent 1, so we know this again is a linear equation in one variable. Next, I'd like to give a couple examples of real contest problems that can be solved using linear equations in one variable. First up, let's take a look at the 2020 AAMC 8 problem number 1. The question reads, what value of x satisfies x minus 3/4 equals 5/12 minus 1/3? So first, let's notice that this is a question about a linear equation in one variable. There is one variable, x, and the exponent on the variable is 1. Next, we notice that in this case, the equation is already given to us, and our goal is to solve it. Let's take a look at another example, the 2018 AAMC 10A problem number 8. The question reads, Joe has a collection of 23 coins consisting of 5-cent coins, 10-cent coins, and 25-cent coins. He has 3 more 10-cent coins than 5-cent coins, and the total value of his collection is 320 cents. How many more 25-cent coins does Joe have than 5-cent coins? Now, we notice that in this question, there is no equation yet. So part of the problem becomes, how do we recognize that we need an equation, and then how do we set up the equation, and finally, how do we solve the equation in order to solve this problem? We'll work through the full solutions of these examples and other contest problems later in this chapter. Before we talk about solving equations, I'd like to first offer a tip for good practice in math about how to represent numbers. Whenever possible, represent numbers as fractions and not decimals, and not mixed fractions and not percents. Fractions, as we're all probably familiar with, is an integer over an integer, and the bottom integer is not 0. Now, we might have heard of a term called improper fractions, where the numerator is bigger than the denominator. I'd like to suggest to you that we discard this concept of improper fractions and treat all fractions, improper or proper, as just fractions. Let's take a look at some examples. So for example, if I have 0.2 as a decimal, I should rewrite that as 1/5. If I have 1.5 as a mixed fraction, I should rewrite that as 3/2. And if I have 30%, I should rewrite that as 3/10. Now, why would we do the extra work to convert everything into fractions? Well, here are 2 reasons why. First is that in fractions we can express exact values, whereas in decimals we can't. For example, in 1/3, 1/3 is an exact value, versus in decimal representation, we would have 0.33333 repeating forever, but that's not an exact representation, no matter how many 3's that we have. Second reason is that fractions allow us to do easier arithmetic. For example, if I have the expression like 3/2 times 1/3, I can see here that we can cancel out the 3 on the numerator with the 3 on the denominator of the second factor here. However, if I had this as 1.5 times 1/3, it's harder to see that I can cancel the terms 3 from the numerator and denominator because I don't have a 3 in the mixed fraction here. So writing every term as a fraction will help us to do the arithmetic much easier. Now, one challenge for those who want to explore a more advanced topic is this. Fractions, which are also known as rational numbers, we know can be expressed as a over b, where a and b are integers and b is not 0. Now the question is, are there numbers that cannot be expressed as fractions? We can now start looking at solving equations. First, we need to know the goal in solving an equation, and that will help us determine which steps to take. So to solve for an unknown, let's say x, the goal is we need to isolate it. We need the final form of the equation to be x equals an expression on the right-hand side, roughly speaking. To put it into precise terms, we need 3 conditions to be true. First is that there are no other terms on the same side of the equal sign as x. So we see here x is by itself the single term on the left-hand side of the equal sign. Second is the coefficient of 1 for x, meaning that x can only have a coefficient of 1, which it does in this case. And third condition is that no occurrences of x on the other side of the equal sign. And now this is important. This tells us that whatever expression we have on the right-hand side, to consider this equation solved, that right-hand side equation can't have occurrences of x in it. So for example, let's take a look at what some of the end goals could look like. First, we have x equals 34. Now this tells us that the equation is completely solved because we know the value of x. The value is 34. Another example could be x equals 3 times 5 halves plus 8. And here we see that we have an expression on the right-hand side that has no occurrence of x in it. The coefficient of x on the left-hand side is 1, and there are no other terms on the same side of the equal sign as x. This is now not a fully solved equation, but it's almost solved because we can evaluate the right-hand side of the equation and to a value. Then we know that value is equal to x. Now we'll look at various techniques to help us achieve the goal of isolating the unknown. First up is collecting like terms. Like terms are terms with the same variable and the same exponent. Now remember, in linear equations, all the variables have exponent 1, so they'll have the same exponent. For example, if I have 3x plus 5x, these are like terms because they both have x and the exponent is the same, 1. In 6x minus 10x, these are also like terms because they have the same variable, x, and their exponents are the same, 1. Now in a more interesting example, we have 3x plus 6 minus 2x. Here, we see that 3x and 6 are not like terms because 6 doesn't have an x in it. But 3x minus 2x, these are like terms because they both have an x and the exponents are the same. So to help isolate the variable in x, we can collect the like terms by performing the operation on the coefficients. So looking at the examples again, in 3x plus 5x, we can collect the like terms to get 8x. Because 3 things plus 5 things, we get 8 things. Similarly, in 6x minus 10x, we can rewrite that as minus 4x by collecting the like terms. In 3x plus 6 minus 2x, here we remember that 3x and minus 2x are like terms, but 6 is not a like term. So we just combine only the like terms. 3x minus 2x, we get 1x, x, plus 6.
Next up, we'll take a look at a few properties of addition and multiplication that may seem obvious, but they're important and worth calling out explicitly to be clear about which operations we're actually performing. We'll work through an example of why these properties are useful afterwards. So first up is the commutative property of addition and multiplication, which says that for addition and multiplication, the order of the inputs does not affect the output. Or in the form of expressions, this looks like x plus y equals y plus x for all x and y. Similarly, for multiplication, x times y equals y times x. Or in plain words, this means that we can switch the order of the inputs for addition and multiplication without affecting the results. We can take a look at a few examples here. 7 plus 5 is equal to 5 plus 7 because both equal 12. Here, 7 times 5 is equal to 5 times 7 and both equal 35.
Another property is the associative property of addition and multiplication. This says that for addition and multiplication, grouping of the inputs does not affect the output. So in terms of expressions, it looks like if I have quantity x plus y and then plus z, that's equal to x plus quantity y plus z, where I perform the y plus z first and then add x onto it. Similarly for multiplication, if I have quantity x times y, then times z, I can rewrite that as x times quantity y times z, where I perform the operation y times z first before multiplying by x. Now why would this be useful? Between the commutative and associative properties, we can see that this can help us to simplify expressions in equations. So for example, let's take a look at this expression, 746 plus 8,394, quantity minus 746. So let's try to simplify this using the commutative and associative properties. First, I can observe that in this bracket here, I can use the commutative property to switch the order of the inputs. So I write it as 8,394 plus 746, then minus 746. Then I'll use the associative property to switch up the grouping of the operator. So here we have 8,394 plus quantity 746 minus 746. And this we know goes to 0, which means that the final simplified expression is just 8,394. Now, this would be much easier than if I had added 746 to 8,394 first and then subtracted the 746 again, as in the original expression. The third property is the distributive property, which involves both multiplication and addition. In words, it says that multiplication can be distributed over addition. As expressions, it looks like if I have x times quantity y plus z, I can expand that into x times y plus x times z. In other words, I'm distributing this x on the outside into this bracket over each term. So for example, if I have 3 times x plus 5, I can distribute this 3 into this bracket to get 3x plus 3 times 5, which is 15. Another example, if I have minus 6 times 3 minus x, I can distribute the minus 6 into this bracket to get minus 6 times 3, which is minus 18, plus minus 6 times minus x to give me plus 6x. Now we have to be very careful here to note that this minus x inside the bracket can be treated as a plus minus x. So we have minus 6 times minus x to get us plus 6x. The sign is very important here. Now, can we go the other way from distributing? And the answer is yes. We call that factoring. So for example, if I start with the expression 3x plus 15, then I can rewrite that as 3 times x plus 5 using the other direction of the distributive property, and also known as factoring. I factor the 3 out of this expression to become 3 times quantity x plus 5. So far, the techniques we looked at, including collecting like terms and using different properties of addition and multiplication, are all for dealing with simplifying expressions, which is an important part of equations. But in order to solve equations completely, we also need to know how to work with the entire equation, not just the expressions contained in it. So here we've introduced the most important concept in solving equations, which is both sides. First, let's observe that there are 2 sides to an equation. There's the left-hand side, which is the expression on the left side of the equal sign, and there's the right-hand side, which is the expression on the right side of the equal sign. And here's the key takeaway. The same operations must be performed on both sides. Now, this is so important that I'll have to say it again. The same operation must be performed on both sides. You may have heard of rules like move the term to the other side and flip the sign, or cross-multiply the 2 sides. Well, in this course, there will be no such things. And I will also encourage you to stick with using this both sides concept instead of ideas like move the terms or cross-multiply. This concept of both sides is not only more consistent rather than memorizing a bunch of rules, but it also reduces the likelihood of making an error. Also, I would say it would greatly help your future higher level math studies. So with that, let's take a look at the details. Let's take a look at this concept of both sides in the case of addition. And remember, subtraction is just one form of addition, so it's included in here as well too. For this first equation, let's look at x plus 3 equals 8. For this equation, in order to achieve our goal of isolating the x, I will add minus 3 to both sides. Remember, in this concept of both sides, we can perform any operation we like as long as the same operation to both sides. So in this case, we perform the addition of minus 3. We have x plus 3 plus minus 3 equals 8 plus minus 3. Now on the left-hand side, we have 3 plus minus 3, which will give us 0, so we're left with x. And on the right-hand side, we have 8 plus minus 3, which will leave us with 5. For the second example, we have the equation y minus 3 equals 8. And again, our goal is to isolate this variable, y. And in order to do so, I'm going to perform the operation of adding 3 to both sides of this equation. So I end up with y minus 3 plus 3 equals 8 plus 3. And on the left-hand side, I have minus 3 plus 3 goes to 0, so I'm left with y. And on the right-hand side, I have 8 plus 3, which gives me 11. And the operation here was that I added 3 to both sides. Next, let's look at both sides in the case of multiplication. Consider this first equation. We have 3x equals 12. Now, in order to achieve the goal of isolating the variable x, I'm going to multiply both sides by 1/3. So I have 1/3 times 3x equals to 1/3 times 12. On the left-hand side, 1/3 times 3 gives me 1, so I'm left with x. And on the right-hand side, 1/3 times 12 leaves me with 4. So the operation here was that I multiplied both sides by 1/3. In this second example here, we have the equation y divided by 3 equals to 12. And in order to achieve our goal of isolating this variable y, I'm going to multiply both sides by 3. So I'm going to have 3 times y over 3 equals 3 times 12. And on the left-hand side, I have 3 times 1 over 3 on the denominator here leaves me with 1, so I'm left with y. And the right-hand side, we have 3 times 12, which gives us 36. So the operation we performed here was multiply both sides by 3. Now let's put together the different techniques that we looked at so far and solve the two equations from the examples in the beginning of the chapter.
Our equation is 3x plus 4 equals 7. So for the first step, I will add minus 4 to both sides. So I will have 3x plus 4 plus negative 4 equals 7 plus negative 4. On the left-hand side, I have 3x plus 4 plus minus 4, which equals 0, so I'm left with 3x. On the right-hand side, I have 7 plus minus 4, which leaves me with 3. Now from here, I can multiply both sides by 1/3. So I will have 1/3 times 3x equals to 1/3 times 3. And on the left-hand side, 3 times 1/3 leaves me with 1, so I have x left on the left-hand side. And on the right-hand side, I have 1/3 times 3, and I'm left with 1. In the second equation, we have 3 times quantity x minus 6 minus 5 times quantity 6 plus 3x plus 7/3 times quantity x over 2 minus 1 equals to 5/2. Now the first step when I see this is I will use the distributive property to distribute the factors outside the brackets into the brackets. So here we go. We have 3 times x minus 6, we expand that to 3 times x, minus 3 times 6 is 18. Then minus 5 times 6 is 30. Then minus 5 times 3x is minus 15x. And the third part here is we have 7/3 times x over 2, so we have 7x over 6 minus 7/3 times 1 is 7/3 equals to 5/2. Next, we'll collect like terms. And we'll do that in a couple different steps. First, we see we have 3x minus 15x, so that will give me minus 12x. And there's another x term here, so we plus 7/6 x. We also collect the constant terms as well too. So minus 18 minus 30, that gives me minus 48. And another minus 7/3 at the end here, and this equals to 5/2. Now we need to further combine the like terms. So these terms both have x, so I will bring them to a common denominator first. So we'll have minus 72x over 6 plus 7/6 x. And again, these two terms are both constants, so we need to bring them to a common denominator. So I have minus 144 over 3 minus 7 over 3 equals to 5/2. Now, we can combine them. So minus 72x plus 7x, that gives me minus 65x over 6. Then minus 144 minus 7 is 151 over 3, and that equals to 5/2. From here, we can now add 151 over 3 to both sides. So we have minus 65x over 6 equals to 5 halves plus 151 over 3. So here we have a constant and another constant on the right-hand side, so we can combine them. So we can write minus 65x over 6 equals, and we'll bring these to a common denominator first of 6. So we'll have 15 over 6 plus 302 over 6. And this will in turn become 317 over 6. Now we can multiply both sides by 6. So we have minus 65x equals to 317, sorry. Lastly, we divide both sides by minus 65, and we're left with x equals to 317 over 65 with a minus sign. And here we have it. We solved the equation to get x equals minus 317 over 65.
Here's a question for our consideration. Once we solve for an unknown in an equation, how do we check if we solved the equation correctly? Well, one way is that we can substitute the value back into the original equation and calculate to see if both sides are equal, as the equation should be.
Let's apply that verification technique to our first example equation. Recall that the equation was 3x plus 4 equals 7, and we had previously solved the equation to get x equals to 1. Now let's use the substitution method to verify if our answer is correct. So when I verify, let me keep track of the left-hand side and the right-hand side separately to see if they're equal. Now on the right-hand side, I know that I have 7, so I'll just put 7 here. On the left-hand side, I have 3x plus 4, and if I substitute x equals 1 here, I have 3 times 1 plus 4. Now this will evaluate to 3 times 1, which is 3, plus 4 is 7. And we see that the left-hand side equals the right-hand side, in which case we know that we solved this equation correctly. Now I'd like to invite you to work out this verification method for the second equation that we solved together earlier on.
Now I'd like to show a common pitfall to avoid when solving equations, and that's dividing by an unknown. Consider if we have an equation like 8x plus 4 equals 5x plus 4. Now the first thing I would do is add minus 4 to both sides. So we end up with 8x equals to 5x. Now from this step we see that we have x on both sides. So we might be tempted to say, why don't we just divide x from both sides? Well, what happens if we do that? So we divide both sides by x, and we end up with 8 equals 5, which is clearly not true, and it looks like we just broke all of the numbers system. So what happened there? Well, we divided by x, which is an unknown, and when it's an unknown, we know it could be 0, in which case we can't divide by it. So instead of dividing by x, what we can do from this step is instead subtract 5x from both sides. So we get 8x minus 5x, so we're left with 3x on the left side. And on the right-hand side, 5x minus 5x gives us 0. And now, from here, we can divide both sides by 3, which is a constant and not a variable. And we're left with x equals to 0. And we see that in this case, indeed, x equals 0. So we could not have divided the x from both sides at this step here. We've seen from a previous example of a contest question where we are not given the equation to solve in the question. Then part of the problem becomes recognizing that we can use equations to solve the problem, and then setting up a suitable equation. To set up a suitable equation, an important step is to decide which value your variable will represent. Here, there are no hard and fast rules, and as you solve more problems and gain experience, you will develop an intuition for which values in the problem are more suitable to be the variable in your equation. And here are 2 guidelines that may be helpful. First is, what value are we looking for in the problem? If we set our variable to be the value that we're looking for in the problem, then solving the equation oftentimes gives us the answer for the problem. The second guideline here is that, is there an easy value to model based on what's given in the question? Depending on the conditions and the information that you have from the problem, certain values may be easier to model into an equation and to solve it. Then that value can in turn lead you to the answer to the problem. Now we'll apply what we learned in this chapter to some real contest problems, starting with two of the examples that we looked at earlier. 2020 AAMC 8 Problem 1. The question reads, what value of x satisfies x minus 3/4 equals 5/12 minus 1/3?
And here we see we're given a linear equation in one variable, and we're to solve it. So the first thing I would do, in order to isolate x, I would add 3/4 to both sides. So I would write x minus 3/4, and I would add 3/4 to the left side, and then I would add 3/4 to the right side. On the left side, minus 3/4 plus 3/4 goes to 0, so I'm left with x. And on the right-hand side, I have some constants that I need to evaluate. So I will first bring them to a common denominator of 12. So 12 and 5 is 5. Minus 1/3, to bring it to 12, I have minus 4. And then 3/4 to bring it to 12, I have plus 9. And this will equal to 5 minus 4 plus 9 is 10 over 12, which can reduce to 5 over 6. So the answer is E.
2018 AAMC 10A Problem 8. Joe has a collection of 23 coins, consisting of 5-cent coins, 10-cent coins, and 25-cent coins. He has 3 more 10-cent coins than 5-cent coins, and the total value of his collection is 320 cents. How many more 25-cent coins does Joe have than 5-cent coins?
In this question, we recognize that we can use an equation to solve this because we're looking for an unknown value, and we're given some information about that unknown value in relationship to other values that we do know. The particular value we're looking for is the difference between the number of 25-cent coins and the 5-cent coins. So in order to solve this, we first need to come up with a suitable variable. Well, we're looking for the difference between the number of 25-cent coins and the number of 5-cent coins. So we may think, well, we can set that as our variable. However, based on the information that we have in the question, that value might not be easy to model. Instead, let's say we let x be the number of 5-cent coins that Joe has. So now we can draw a little chart here. We know that the number of 5-cent coins we have is x, and we'll model the other coins as well too. So we have 10-cent coins, which we're given in the question that he has 3 more 10-cent coins than 5-cent coins, so that will be x plus 3. And the number of 25-cent coins, well, we're given that we have in total 23 coins. So if we take 23 and we subtract off the number of 5-cent coins, which is x, and the number of 10-cent coins, which is x plus 3, this should leave us with the number of 25-cent coins. So to simplify this expression here, we can expand the bracket here to get minus x minus 3, and collecting the like terms, we'll have 20 minus 2x of 25-cent coins. Now, we need to come up with an equation using this variable. We're given one more piece of information that the total value of the collection is 320 cents. So let's try to model that based on the information that we have from x. So we know that the total value of the 5-cent coins should be 5 times x, because that's the number of coins. And then we can add on the total value of the 10-cent coins, which is 10 times x plus 3. And similarly, we'll add on the total value of the 25-cent coins, which is 25 times 20 minus 2x. And now this should be the total value of all the coins, which equals 320, as given in the question. Now we have an equation. To solve this, we might be thinking, well, we can first just expand the two terms that we have with brackets. However, we notice that we have a factor of 5 on both sides. And when possible, we should always try to reduce so that we can be working with smaller numbers. So my first step here, I will multiply both sides by 1/5. So I have 1/5 of 5x plus 10 times x plus 3 plus 25 of 20 minus 2x equals to 1/5 times 320. Now simplifying this, I have 1/5 times 5, distributing this in, will leave me with 1, so I have just x left, plus 10 times 1/5 is 2 times x plus 3 here still, plus 1/5 of 25 is 5, and I have 20 minus 2x left here. And on the right-hand side, I have 1/5 times 320, which leaves me with 64. Now I can go ahead and expand the left-hand side and collect the x's together. So I have x plus 2x plus 6 plus 100 minus 10x equals to 64. On the left-hand side, I'll collect the like terms together. So we have x plus 2x minus 10x. So that means we have minus 7x altogether, plus 6 plus 100 is 106, and that equals to 64. Now, we can add 7x to both sides and subtract 64 from both sides. And we'll do this in one step, like this. So we have 7x minus 64 from both sides, and then minus the 7x plus 106, which will equal to 7x minus 64 plus 64. On the left-hand side here, collecting like terms, we have 7x minus 7x, which goes to 0. Then we have 106 minus 64, which leaves us with 42. And on the right-hand side, we have 7x minus 64 plus 64, and the second and third terms go to 0 together. So we're left with 7x. Here, we can now multiply both sides by 1/7 to isolate for the x, and we're left with x equals to 6. Now we have our value for x. And remember, in the beginning, we set x to be the number of 5-cent coins. Now we look back at the question and see what value we're looking for. So we have the number of 5-cent coins, and we need the number of 25-cent coins. And we said the number of 25-cent coins was 20 minus 2x. And substituting in the value of x equals 6 here, we get 20 minus 2 times 6. And 2 times 6 is 12, and 20 minus 12 is 8. So this means that Joe has 8 25-cent coins. The answer we need to find is the difference between the number of 25-cent coins and the number of 5-cent coins. So we have 8 minus 6, which is 2. And the answer is C.
2018 AAMC 10A Problem 6. Sungho uploaded a video to a website where viewers can vote that they like or dislike a video. Each video begins with a score of 0, and the score increases by 1 for each like vote and decreases by 1 for each dislike vote. At one point, Sungho saw that his video had a score of 90, and that 65% of the votes cast on his videos were like votes. How many votes had been cast on Sungho's video at that point?
In this question, we again need to come up with a suitable equation with a suitable variable defined. The question asks us to find how many votes has been cast on the video at this point. So let's let that be our variable. So we'll say let x be the total number of votes. Okay, so now we have a variable, and we need to come up with an equation. We're told that 65% of the votes on the video are like votes. And as per our good practice, let's convert 65% into a fraction first. So 65% is equal to 65 over 100, which equals to 13 over 20. Now for our equation, let's write it in terms of the total score on the video so far. So we know that 13 over 20, or 65%, times x, so that many of the votes are like votes, and for each like vote, we have a score of 1. So I'm going to multiply that by 1. And now we add on the score from the dislike votes. So we know that each dislike vote gives us a score of -1. And how many dislike votes are there? Well, it's the remaining votes. So that would be 1 minus 13 over 20 of the total number of votes, x. And together, this should give us our current score of 90. Now we have this equation, and we can go ahead and solve it using the techniques that we looked at. First, we can combine some factors here. So 1 times 13 over 20x just leaves us with 13 over 20x. And here we have some constants. So we have -1 times 1 minus 13 over 20. So 1 minus 13 over 20 leaves us with 7 over 20. And times a -1 gives us a minus 7 over 20. So we'll have a minus 7 over 20. And we'll still have the x, and this equals to 90. Now, we can combine like terms here. We have 13 over 20x minus 7 over 20x leaves us with 6 over 20x, which is 3 over 10. X equals to 90. So now we can solve this first divide both sides by 3, and then multiply both sides by 10. So we get x equals to 300. And that leaves us with 300 being the total number of votes, and that's exactly what we're looking for in the question. So the answer here is B.
2019 AAMC 8, problem 16. Tiang drives 15 miles at an average speed of 30 miles per hour. How many additional miles will he have to drive at 55 miles per hour to average 50 miles per hour for the entire trip?
For this question, we first need to be familiar with the relationship between speed, distance, and time. And that is, average speed is equal to total distance over total time. So now we can look at the question and set up a suitable equation. We know that we're looking for the additional miles he has to drive at 55 miles per hour to average 50 miles per hour for the entire trip. So let's let that value be our variable. So we can say, let x be the additional miles. Now, let's try to set up an equation in terms of x. So we know the average speed that we're trying to achieve is 50 miles per hour. So that's going to be our left-hand side here. On the right-hand side, we need the total distance traveled, which will be the 15 miles that he already traveled, plus the additional miles that he will travel, which is our x, and that should give us the total distance. For the total time, for this one, we need to see how much time he has already traveled for, and we can calculate that by taking the distance that he's traveled so far, 15, and divided by the speed that he traveled at, which is 30. So that's the initial time for what he already traveled, and now we need to calculate how much time he will travel the additional miles. So we can add on the additional time here, which would be x divided by his speed that he will go at, which is 55. So now we have an equation in terms of x. And first step here is I'm going to simplify some of these constants here. So here we have 15 plus x, which doesn't change. And then 15 over 30, I know that equals to 1 over 2 after we divide the numerator and denominator by a factor of 15. And the x over 55 is a constant here. Now let's go ahead and try to solve this equation. We have 50 equals 15 plus x over 1/2 plus x over 55. So the first step here is I'm going to multiply both sides by this denominator value of 1/2 plus x over 55. So I'm going to have 50 times 1/2 plus x over 55. And that's going to equal to, when I multiply the right side here by this denominator, I'm going to be left with just the numerator. So our equation now looks like this. And from the left-hand side here, we can expand using the distributive property. So we have 50 times 1/2, which leaves us with 25, plus 50 times x over 55. And 50 over 55, we can simplify that to 10 over 11x by dividing through a factor of 5. And that's equal to our 15 plus x on the right-hand side here. Now, we can subtract 10 over 11x from both sides and also subtract 15 from both sides. So we'll end up with 25 minus 15 equals to x minus 10 over 11x. Collecting the like terms here, we'll have 25 minus 15 is 10. And on the right-hand side here, we have x minus 10 over 11x will leave us with 1 over 11x. And jumping over to the right side here, we can solve this last line here by multiplying both sides by 11, and we're left with 110 equals x, or x equals 110. And here we see what x represented. It was the additional miles that he had to travel, which is exactly what we needed to find in this question. So therefore, 110 is the answer, and we can circle D here.
And that's the end for Chapter 2. In this chapter, we covered linear equations in one variable, techniques to solve them, and some applications of them to real contest problems. While the techniques we looked at can be quick to pick up, it will take a lot of practice doing a lot of questions to become proficient with them in a contest setting. Oftentimes, the biggest obstacle in contests is time, So besides solving the equations correctly, I highly encourage practice to solve them quickly and efficiently as well too. In the next chapter, we'll continue looking at linear equations, but this time with multiple variables. So stay tuned for systems of linear equations.